Hi, everyone. Let's start the second plenary talk now. So it's my great pleasure to introduce Professor Malabika Pramanik. Dr. Pramanik received her PhD in mathematics from the University of California at Berkeley in 2001. After short-term positions at the University of Wisconsin, University of Rochester, and California Institute of Technology, she joined the University of British Columbia faculty in 2006. She was appointed the director of the Banff International Research Station for Mathematical Innovation and Discovery in 2020. Dr. Pramanik's awards include the Ruth E. Michler Memorial Prize from the Association for Women in Mathematics, the Krieger Nelson Prize from the Canadian Mathematical Society, a Killam Research Award, and a Killam Teaching Award from the UBC Faculty of Science, a 2018 Wall Scholarship, and a 2019 Simons Fellowship. She was named a Fellow of the Canadian Mathematical Society in 2018 and a Fellow of the American Mathematical Society in 2022. Today, Dr. Pramanik will be speaking on circles, projections, and operators.
Hi, everyone. Can you all hear me? Okay. At the back too, right? Okay. And how about this? If I set my microphone away and speak here, it's still audible? Okay. So I'm going to get started, and I'll try my best to write bigger. This is my first time with this technology. I was prepared for a chalk talk. So I should tell you that the potential for technological disaster is high. Let's see how this goes, okay? So first off, thank you, IOTA organizers, and especially Ian and Marina for the opportunity to be here with all of you today, and most importantly, to bring us all together on this beautiful campus for this week-long celebration of operator theory and applications. My talk today is going to have two parts. In the first part, I'll be discussing two problems sitting at the interface of geometric measure theory and harmonic analysis. And these two problems are quite unrelated. At least they seemed entirely independent to me at first glance. But in the second part of the talk, I'll try to make the case that there is this one geometric operator that holds both of them together. Okay? So let's get started. So here's a result due to Besikovich and Rado and independently Kinney in 1968. And what they proved is that there exists a closed set E, subset of the plane, that contains a circle of every radius and has Lebesgue measure 0. Okay. So, on the face of it, this is an extremely counterintuitive statement, because the fact that this set has Lebesgue measure 0 suggests that this set is small, at least in the sense of Lebesgue, and yet it contains a circle of every radius. And if there is one thing that we know about circles, if they are distinct, then they can intersect in at most 2 points. So this set has many, many points, and yet it is small, so where exactly are these points going? So my first question for today how large is this set? So let's go back, and we are going to give this set a name. We are going to call this a Besikowicz-Radokiny set. So we are going to call this a BRK set. By the way, Besikowicz and Rado's construction, although not Kinney's, at least not directly, it extends to RD for D greater than or equal to 3, and circle is, of course, replaced by a sphere. Okay. So my first question here is, how large is a BRK set? And I know it's not a mathematically rigorous question because I haven't told you what large means. All right. And I want to, at the same time, since we are talking about problems, I want to tell you about a second question. And if it doesn't look like anything similar to what we have talked about thus far, well, certainly you're not alone. Here we go. So I want to talk about projections. There we go. Okay. What do I mean by projections? So let's start with a really, really simple concept, projection of a point on a line. So here's, let's say we are in RD, in any dimension, and a point X is sitting inside of RD, and we have a direction V It's a vector of unit length. So all I'm going to do is project X in the direction of V, so that this is perpendicular, and I want to call this distance PV of X. So this is nothing other than, so PV of X is the projection of V in the direction. And one of the things we learn right at the beginning in multivariable calculus is to come up with a formula for it. So if this is the angle phi between X and V, this is nothing other than the length of X times the cosine of phi, otherwise known as X dot V. Okay. So what's the question? So the rudimentary question is, suppose we have a bunch of points, a set with lots and lots of points. So this is my set A. So A is a subset of RD, large. And what we want to check is the size of its projections, PV of A, which is simply all the projections in one direction thrown into a set. So as X ranges over A, we look at all its projections, PV of X in a fixed direction V. And the question is, if A is large, how large are its projections? So question 2, if A is large, how large are its projections? Okay. Now, there are some easy deductions we can make. And once again, you see there is that funny word, large, which we know English-wise but haven't described math-wise. We'll get there. So the intuition is that if a set is large, then most of its projections must be large, if not all. So we expect most projections. What do I mean by that? What I really mean is that we expect PV of A to be large for most, but not all, V. And why? What's the reason? Well, here's a simple example. So let's say your A is a vertical line, and your V is the horizontal line. So here's a lot of points sitting on this line, which drops into exactly just one point, and that's an example of an A and a V, where A is large, but V is measurably small. Okay. So these are two questions. One is the size of the BRK set, and the other one is the size of projections of a large set that for the moment, for this talk at least, we are going to focus on today. Before I go any further, I need to tell you what I mean by large, because I can't keep on saying large and large and large and not tell you what I mean by that. So for many of you, this concept may be something that you work with every day, but some of you may not. So I'm going to describe to you what I mean by large, at least for this talk. So the world of geometric measure theory abounds in many different notions of sizes. For this talk, at least, I am going to just fix one of them, and that's the notion of Hausdorff dimension. Okay. So what exactly is the Hausdorff dimension of a set? So please bear with me, because even though the definition, the initial stages is kind of forbidding, it's truly a ubiquitous concept and very relevant for what we are going to discuss today. So what do we do? So we are going to start with a Borel set A in RD, and we are going to go through a series of steps. So let's say if this is the set A, we are going to cover A by balls of radius at most delta. So we are going to look at all possible coverings of A by a countable union of balls centered at some xj, radius rj, and what we require is that all these radii must be smaller than or equal to delta. Okay? And for every single cover of this type, I will create this sum rj to the power of s. What is s? S is an exponent between 0 and d. Okay? Now, let's take the infimum over all such covers, and you will realize that this infimum is monotone in delta, and we take the limit as delta goes to 0. Okay. So, this object is what we are going to define as the S-dimensional Hausdorff measure of A. So this is the S-dimensional Hausdorff measure of A. Okay. Now, Hausdorff measures have this property that if you take, let's say, try to draw a picture with S on one side and the Hausdorff measure of a set A on the other axis, it has this property that for a while it's actually infinite, and then it kind of drops off a cliff and becomes 0 after that. So, and it ends at D. So this drop-off point here, this is what we call the Hausdorff dimension of A. And as you can see from its definition, it's the supremum of all exponents S such that the S-dimensional Hausdorff measure is infinite, and it's the infimum over all exponents S such that the S-dimensional Hausdorff measure is 0. Okay. So this is the object that's going to be my notion of size for this talk. Why do we have to go through this contortion? Well, many reasons. First of all, these are Borel measures. So all measure theoretic properties belong to them. First of all, as sanity checks, the notion of Hausdorff dimension actually agrees with our notion of topological dimension for most geometric objects. The Hausdorff dimension of a line is still 1, and the Hausdorff dimension of a surface is still 2, so that's great. But its real power is in the fact that it can lend a notion of size to objects that are very, very rough. So things for which differential geometry gives up, Hausdorff dimension is able to offer a notion of size. So for example, the dimension of the Cantor middle third set is log 2 over log 3. If you look at the Sierpinski triangle, it has Hausdorff dimension log 3 to the base 2. If you look at the graph of the standard Brownian motion, the graph has Hausdorff dimension 3/2 almost surely. So this is a really nice notion to have to measure size. Okay, so with this in mind, let's go back and revisit all our old questions. When we talked about how large is a BRK set, what we really meant is what is the Hausdorff dimension of a BRK set. Okay. And the first result in this, for those of you who are actually familiar with the Kakeya problem, you are going to actually recognize this as a circular variant of the Kakeya problem. And the Kakeya conjecture remains open to this day. Thankfully, the BRK problem has a happier ending. So we actually know what the result, what the size of a BRK set is, and this is due to, so these are the two people who have contributed to this particular question. So Kolasa and Wolf. For D larger than or equal to 3, and Wolf for D equal to 2. And this is during the period of 97 to 99. And the result is that every BRK set must have Hausdorff dimension D. And this is the BRK set in our D, of course, so this is just to say that the set must be full dimensional. Okay. Let's go on to our second question and try to sort of rigorize that statement here. So our question was, if A is large, how large are its projection, PV of A? Okay, so So the one result here that's important to know, because everything else that I'm going to say builds off of it, it's called the Marstrand projection theorem. And it makes precise what intuition says. So suppose that it has a really very fine statements built into it, but I'll just keep things simple for now. So let's take A in our D at least 2, A is always Borel. So the Marstrand's projection theorem says the following, that if you look at the Hausdorff dimension of the projection, then this is actually equal to the minimum of the dimension of A and 1. So basically what this means is, if the dimension of A is, let's say, strictly larger than 1, then if you project on a line, it's just going to pick up a full dimension of 1, and this is for almost every V in the D minus one-dimensional unit sphere. Okay. So there are, as I said, finer statements, but I'm not going to go in there. Rather, I'll try and unpack what this statement, almost every V in the D minor dimensional unit sphere in our D, what it actually means. So what it means is that if we look at the Marstrand projection theorem statement, that this statement could fail on an exceptional set scripty, whose measure is 0, and what is sigma d minus 1? This is the surface measure on the sphere. Okay. So that's the sort of the baseline, the gold standard in the field against which everything is referenced. And this brings us to this question of restricted projections. In other words, what we are going to be interested in is precisely this exceptional set, and we are going to look at projections on certain exceptional sets and ask ourselves, does a Marstrand-like projection theorem continue to hold on certain exceptional sets? So let me try and explain this in the context of an example. Okay. All right. So what do I mean by exceptional sets? This is a refined question. And I'm going to restrict myself to d equal to 3 and ask myself the following question. So here's an example of an exceptional set. So let's take a curve gamma, which is defined on an interval j and maps into the unit sphere in R3. So this is a C2 curve. Okay. And what I want to, so I want to look at the image of gamma, and I want to observe that if you look at the surface measure of this is a 0 set. Which means that the Marstrand projection theorem has absolutely nothing to say about projections that take place on these directions of curves. So I'm going to try and draw a picture. Okay, so this is S2. And think of a curve, let's say, that is sitting on the sphere like so. This is gamma, okay? And I want to look at projections along the directions of gamma. So the projections, these are the different v's. So I want to look at projections in the direction of gamma theta, and just to make the notation less cumbersome, I'm just going to call it pi sub theta of x. Okay? So the refined question, so this is question 2 prime, is there an MPT-like theorem for these curves gamma j? What does that mean? That means that as we take projections, is it true that for most points on these curves, the projection will be at least as large as dictated by the dimension of the set A? So this is the question, and almost immediately we know that, well, it can't. The way I have stated it, it's a bit too good to be true. So the answer, the easy answer, is not always. And what's the example? So let's take a look at the case where gamma is the great circle, cosine theta, sine theta, 0. And what's A? A is the vertical line, 0, 0, x3. Okay? So the Hausdorff dimension of A is 1, but if you look at pi theta of A, which is the projection, so this is nothing other than gamma theta dot A, this is identically 0 no matter what theta is, so the dimension of every single pi theta is 0. So no hope of an MPT-like theorem if the question is posed for a general curve. However, if you do decide to tweak this example a little bit, for example, let's say instead of, let's say, cosine theta, theta, sine theta 0, let's say we looked at a curve which is not exactly the great circle, but a little bit off. So for example, let's say 1 over root 2 cosine theta, 1 over root 2 sine theta. So it's off of the great circle. Then certainly we don't know, so this does not, at least the same argument doesn't work. So for this particular case, if we call this gamma tilde, so what is gamma tilde theta of A? It's actually not as easy to figure out, and there remains the hope that maybe an MPT-like theorem may be possible in such cases. Okay, so that's really the whole goal of this restricted projection talk, which is to identify a certain non-degeneracy condition on these curves, which will allow a Marstrand-like projection theorem. And let me state what that result is. Okay, so what's the non-degeneracy criterion? Okay. So we are going to say that gamma is non-degenerate if, when you look at the span of gamma, gamma dot, and gamma double dot, this is R3 for all theta in J. So another way of saying it is if you look at the determinant of consisting of the matrix gamma, gamma dot, and gamma double dot as the three columns, then the determinant is bounded away from 0 for every theta in J. It turns out that the not great circles, they all obey this property, and the theorem is the following. That for gamma obeying star, we do have an MPT-like theorem, and in fact, let me sort of try to state this properly. So the dimension of pi theta of A is indeed the minimum of dimension of A and 1, and this is for almost every theta. And B, we actually have some statements regarding the exceptional set. So if you look at the dimension of the set of thetas for which too many dimensions. So if you look at the set of thetas for which dimension of pi theta of A is less than or equal to S, then that's strictly smaller than S, then that's less than or equal to S, and that's for all S. So this is actually telling you something about the size of the exceptional set where this dimension happens. But for now, if you like, you can just simply focus on this statement. This is really the MPT-like theorem that we were aiming for. Okay. So this was originally a conjecture due to Fassler and Orponen. So this is Fassler and Orponen. It's a conjecture. And this conjecture was verified for a special case by Kainmaki, Orponen, and Venieri for especially this curve that I just told you about, this curve. And so this was proved in a special case. And between 2022, this is for gamma tilde, the special case, and between 2022 and 2024, there has been a flurry of activity on these restricted projection problems. So in its current form, for general C2 curves obeying this property star, this is a result on one hand joined with student Tonggu Yang and a colleague Josh Zhao. And there was a different proof using different techniques by Shengwen Gan, Larry Guth, and Dominic Muldag. Okay, so let's summarize where we are right now. So I posed two questions in geometric measure theory. One of them had to do with sets containing lots of circles, and the result there is that it must have Hausdorff dimension D. A different problem is this question about restricted projections, especially projections that are taking place along directions lying on a C2 curve obeying certain non-degeneracy criteria. And I have presented some results on each one of them, and that's all I have done so far. So far, there is no operator in sight. So if I'm going to redeem myself in an operator theory workshop, I have to, at some point, show you where the operator theory is. Okay, so I'm going to take a quick break and see if there are any questions so far. Okay. All right, so here we keep going. So where's the operator? Okay. All right, so I better put it down first. So the operator that I'm going to work with looks something like this. So let's denote by C sub delta of XR the following set of points Z in RD with the property that Z minus X, its length is between R plus delta and R minus delta. In other words, this is nothing other than a delta thickened sphere. With radius, so centered at X, radius R. And I should tell you a little bit about how this R and delta are related. Delta is really, really small compared to R, so you can think of, let's say, R between half and 2, and delta really tiny, really, really small. Okay. Now, with this notation, the maximal operator in question is the following. So we are going to define an object m delta f of x, or f of r. Okay. So what is f? F is an input function. It's d-variate, so it takes a function of d variables into the real line. And I'm defining this operator as the supremum of certain averages. Okay, so this is my operator. And what am I taking the supremum over? I'm taking the supremum over all x's in RG. In other words, you take your absolute value, average it over all possible delta spheres of radius r, and whatever is the maximal value, that's your m delta f of r. Okay? So when there's a lot of things that are known about this function, this is called a circular maximal function. When d is equal to 2, it's called Wolff's circular maximal function, and this is what some basic facts that are known about this. So here's the theorem, and this goes back to, again, Kolasa and Wolff for d larger than or equal to 3, and to Wolff for d equal to 2. That this m delta maps, well, I might as well write down what the equation is. If you are looking it maps L2 to L2 with a logarithmic blow-up factor. Okay. And this is for d larger than or equal to 3. And when d is equal to 2, we have a very similar statement, but with L3 instead. So for every epsilon positive, one can find an A sub epsilon such that this statement is true. Okay. So in the time, 10 minutes or so that's left to me, what I want to prove to you is that these operator theoretic statements about the circular maximal operator is what both of those two geometric problems have in common. On one hand, these results, part B, for d equal to 2, because everything that I'm going to be talking about is specific to this particular result. On one hand, this gives you the Hausdorff dimension of the BRK set in the plane, and indeed this was one of the corollaries of the work of Wolff, and before that of Colas and Wolff. But more recently, in these restricted projection problems that I was talking to you about, this is exactly the same statement that pops up for some weird reason. Because, and this is, for me at least, truly weird, because when we look at restricted projections, there does not seem to be any circles in sight, right? So in these last 10 minutes of the talk, what I intend to do is to tell you what does this circular maximal operator, what does that have anything to do with restricted projections? Okay. All right. So in order to really understand the connection, it helps to look at this operator theoretic statement, but boil it down to an equivalent characterization so that we can start to see some connections emerging. Okay, so let's talk about an equivalent characterization of Wolff's circular maximal theorem. So the statement that I'm going to tell you now is an alternate rendition of the same L3 to L3 statement that I stated in my earlier page. So let me try to go over this one carefully. So suppose you are given, so script C is a family of circles. In the plane, and with delta separated radii. Okay? And we are going to fix an arbitrary eta positive and a really, really small delta. Okay. Then, this equivalent characterization that I was trying to tell you about, so let me get my quantifiers right. So the way I think about it is as follows. So let me write it down first and then tell you about it. Okay. I can find a sub-collection script A of my family of circles such that this following relation is true. See, if we look at all the circles, all the points in C delta, and I need to define to you what this object, this multiplicity function is in a moment. So I know there is a lot of parameters, but bear with me because my hope is to kind of explain what all of this really is. this will be true for all C inside your family, and for all sufficiently small lambda. And I still need to tell you what is this M delta. M delta is really the multiplicity function which tells you the number of circles in the family such that X lies inside C delta. Okay. So let me try to unpack this for a moment. And I haven't told you that I said there's a big set, and I haven't told you yet how big it is. So maybe I should do it now. So the size, the cardinality of A is at least half the cardinality of script C. So if you're trying to think what on earth this inequality is trying to say, it says that there is a large subset of the circles for which the proportion of points with high multiplicity is small. And I'll draw this, so the way I try to remember this is through this English. So high multiplicity points can occur. And in fact, this is how I'm defining points of high multiplicity, where the multiplicity function takes a really, really large value. But the proportion of high multiplicity points, but the proportion of such points in most circles is small. Okay. And it's always good to keep one.
So should it be for all C in script A?
No, it's actually all C in script C.
So where is script A in the statement?
Oh, so there is script A in. Oh, I'm sorry. So then for all A in this one should be script C. Is that what you meant? This one?
Yeah.
Yeah. Sorry, you're right. Thank you. Okay, so this one is script A, this one is script C. Sorry, thank you. Okay, let's keep going. So here's a picture. So let's take a look at a bunch of circles. This is often called the clamshell configuration for reasons that you can see. Okay. So this is a family of circles. Look at this point. This point is clearly of a high multiplicity. Okay. But notice, so absolutely there can be high multiplicity points because every single circle is going through this point. However, if you look at all the other points, they have multiplicity 1. Okay, so this is really what Wolff's statement was trying to say. So let's go back to this, and it turns out that this rendition of Wolff's circular maximal theorem is really what is key to also the restricted projection problem in a different formulation, because it turns out that this statement is not just true for circles. This is actually true for families of non-degenerate curves, where non-degeneracy is defined, among other things, in the same way that I told you previously. Okay? And I'll leave you with a picture, because I'm almost out of time, so I can't really go too much into the details. So here is how this enters into the picture for restricted projections. So let's say that this is theta, and on this side we are going to do pi theta of A. Okay. So let's draw a curve. What is this curve? This curve I'm going to call gamma z, and this is nothing other than the set gamma theta dot z, where z belongs to some this set A. Okay? So even though the original restricted projection problem was happening in R3, after we have projected it down, for every z, we are going to get a curve on the plane. So I'm going to draw a few more. So this is, let's say, gamma of z1. And here is gamma of z2. Okay, so really what we have is a family of uncountable non-degenerate curves on the plane. That's the critical point, that the non-degeneracy condition of little gamma makes these curves non-degenerate in the sense of this family of circles, this statement that I talked to you about. Now, here is sort of a one-line, I don't know, demi-proof, if you will. So let's draw this line, a vertical line at the point theta. Let's call this vertical line L theta. Then all the points that get picked up, these are precisely, if you look at L theta, intersected with so what you end up getting, these are precisely pi theta of A. Okay. If it turns out that we expect that this size, these intersections, will have large dimensions for most theta. What happens if the dimension of such an intersection of these points is small? What it means is that all of these curves, they are flowing through each of these vertical lines. If this dimension of these intersection points is small, that means all these curves are somehow zeroing in on these few points and passing through them. And the more such lines there are, that means that these points are become high multiplicity points, and having high multiplicity points for many thetas simply contradicts this meta principle that I told you, that high multiplicity points can occur, but the proportion of such points on most curves is small. So we expect that high multiplicity points that occur along these vertical lines, they have to be spread out, they have to be very sparse, otherwise that meta principle that I talked about will get violated. Okay, so I know I'm out of time, and I'm going to stop. I'm sure you have questions, and we'll take it from there. By the way, before I end, if you like this genre of geometry and analysis interaction with these rich contributions from operator theory, I want to give a shout out to this special session S1, which is being co-organized by Jennifer Duncan and Alan Chang, and they are, among others, architects of some of the main results in this field, so please join and talk to them if this is something that is of interest to you. Thank you very much.
Thank you very much for the very nice talk. Are there any questions for Malabika?
I guess I could ask how this original work, physical vision, how the construction, what kind of construction they feel.
So There are many, this construction is, by now, there are several different constructions of BRK sets. The Besikovich-Radu construction was somehow got its inspiration from Besikovich's own work about Besikovich sets for circles. Kinney's construction, this one is simple, but then doesn't generalize easily. It appeared in American Math Monthly in 1968. So maybe that's a better place to start. The Besikovich-Radu case had to do with geometry of circles, taking a circle of one radius and then trying to impose a circle of another radius so that the intersection is large, so that the measure keeps on becoming small. It's an interesting read, but I think maybe the Kinney's construction is the better place to start because it's easier to understand. Yeah.
You replace circles by triangles, things won't work.
Sorry?
You replace circles by triangles.
Yes.
It won't work.
Okay, so let me repeat the question. The question was, if we replace the circles by triangles, will this work? And this won't work, as you said. It's not going to work because that non-degeneracy condition is not going to be satisfied. So it is not going to work for triangles or polygons or things with flat edges.
Any other question?
There's one over there.
On page 14, what is C delta?
Page 14 over here. This one? Okay. So I think it's over here somewhere. Let me see. It was quite a few pages back. So C delta was the delta thickened sphere C. So if C is the sphere, CXR was a sphere with center X, radius R, and C sub delta is the delta thickened version of that sphere.
If there are no more questions, let's thank Malabika again.